Hello, this is John Miyares, and you will be happy to know that there are only two videos left for you to watch in this course. These last two sections, coming from Chapter 10, cover material that I consider to be some of the easier material we're going to cover this year, or even if it isn't easy, most of this is material that you have at least seen before in a previous math course, which is one of the big reasons why I rearranged the topics in this course to have these sections taught last. I'm assuming that most everyone in this class has worked with systems of equations in a previous algebra class before. The content from section 10.1 is taught in most first-year algebra classes, and the technology has advanced to the point that the material we're going to be looking at in section 10.3 is going to be pretty much done exclusively on the calculator. Now, the one thing I do want to point out before we begin this lesson is that the material we are covering here is not going to be on Quest 6, but will only be covered on the final exam. And even then, it will only be on one, maybe two questions total. So we're covering something called systems of equations. A system of equations is a collection of two or more equations with the same number of unknowns. In this section of the textbook, we are going to limit the scope of our problems to focus on systems with two equations involving two unknowns. A simple example is given here where you're told x plus y equals 6 and x plus y equals 2. In solving a system of equations, we want to try to find values for each of the unknown variables x and y that will satisfy every equation in the system. The equations can be linear or nonlinear, but for this section, everything will be a linear equation, means my powers of x and y will be just to the first power. So in plain English, what we're being asked to do is find the values of x and y that will satisfy both equations simultaneously. The reality is that there are an infinite number of ordered pairs that x and y can be that will add together to give you a sum of 6. You could take 0 and 6, 1 and 5, 2 and 4, 3 and 3, or even go in the negative direction to have -1 and 7, -2 and 8, and several other possible choices. Similarly, there are an infinite number of pairs of numbers that you can group together whose difference is 2. 2 minus 0, 3 minus 1, 10 minus 8, and so on. However, there is only one pair of numbers x and y such that the sum of the two numbers x and y will equal 6, and the difference between the two numbers x and y will equal 2 at the same time. In this lesson, we're going to focus on the different strategies one can use to solve systems of equations like these. Then we will consider some word problems that incorporate systems of equations as a solution strategy. Back in algebra, or some other previous math course, you should have been taught 3 different ways to solve equations like these. So hopefully, for all of you, this is going to be review. The first approach was called the graphical method, and it involved graphing equations of two lines and looking for their intersection point. So let's start with a piece of graph paper, perhaps a graphing utility like Desmos, and let's try graphing the two lines. Desmos makes this method especially easy because you don't need to put the equations into y equals form before graphing them like you would on your calculator. And once the two lines are graphed, it can very quickly find that intersection point for you. In this case, the intersection is at the point 4, 2, which means that the solution to the system will be x equals 4 and y equals 2. Connecting back to the original equations, we can see that 4 plus 2 equals 6 and 4 minus 2 equals 2. Graphically, We've worked with this idea of the golden rule of graphing all semester, where I've said that any point on the graph needs to be a solution to the equation. In this case, what we have is an intersection point for both lines. So this point is on the graph of both lines, so it must represent the simultaneous solution to both equations. The second approach is something called the substitution method. In this approach, you first want to solve one of the given equations for either x in terms of y or y in terms of x, whichever seems easiest. So suppose we start with the equation x plus y equals 6. We could turn this into y equals 6 minus x, or we could turn it into x equals 6 minus y. It doesn't really matter which. But for our sake, since I've already turned it into y equals 6 minus x, let's just leave it this way. Next, we want to substitute the known expression into the second equation to solve for one of the variables explicitly. What we're doing here is something in algebra that is called the law of transitivity. If I know that x minus y equals 2 and that y equals 6 minus x, then we can replace the y in the equation x minus y equals 2 with the expression y equals 6 minus x. This is possible because the x and the y that I'm talking about in both of these equations is really supposed to be the same value. That to say x minus y equals 2 and y equals 6 minus x, I should be able to replace this expression in for y in the second equation. Distributing and combining like terms will give us 2x minus 6 equals 2, which if we move over the 6, we'll get 2x equals 8. Then we can divide everything by 2 and be left with x equals 4. Next, we'll go back to our first equation and substitute in x equals 4 in order to solve for y. So now we'll say 4 plus y equals 6, which when subtracting the 4 will give you y equals 2. This is consistent with what we already saw on our graph. The third approach is called the elimination method, which is also called the linear combinations method. This is where you may need to multiply one equation or the other by some constant, which will allow one set of coefficients to be the same or the opposite of each other. This method is often used when graphing is impractical and substitution is inconvenient because isolating one of the variables creates some pretty ugly fractions. Once we have a set of coefficients lined up, we can combine the two equations by addition or subtraction to eliminate one of the variables. Now for this problem, the coefficients of all of the variables are either -1 or +1. So we could take these two equations and add them to each other right away, which will make the y's fall out, giving you 2x equals 8, which then we can divide both sides by 2 to get x equals 4. Then, just like before, after we've solved for the one variable, we can use that answer in one of the equations to solve for the other unknown variable. In this case, we can plug in x equals 4 into the first equation to get 4 plus y equals 6, which will simplify to y equals 2. So those are your three methods for solving a system of equations with two equations and two unknowns. You have a graphing method, the substitution method, and the elimination method. Let's do some examples. For the first example, we'll use the graphical method. Here, we want to sketch the two lines represented by the equations y equals 2x minus 3 and y equals -3x plus 2, and then we want to determine their intersection point, because that intersection point will represent the solution to the system of equations. In order to do this most effectively, I'm going to pull out my graphing calculator. So first I'm going to check my modes and make sure I'm not in polar mode or parametric mode or anything that could throw off our ability to graph equations the way we expect. So it doesn't really matter that I'm in degree mode. I will set this to real, but the most important part is that we are in function mode. Now I'm going to press the y equals button, and I'm going to enter my two equations. I've got y equals 2x minus 3, and I've got y equals negative 3x plus 2. Now, before I can graph these equations, I will need to set my window first. The easiest way to set a window with these problems is to use Zoom Decimal if you haven't already run the program defaults in order to set your modes and your windows together. So I'm going to use Zoom Decimal. This option, Zoom Decimal, is going to give me a pretty good tracing window for values that I know are going to be pretty close to the origin. So now when we do this, I see the two lines. I can hit the trace button here, and then I can follow the two lines until I can see the intersection. There it is, which will be at the point, at least appearing, x equals 1, y equals negative 1. I can verify that this is the solution of the system in multiple ways. One, if I use the up and down arrow to jump back and forth between the two graphs, notice that my x and my y values aren't changing, whereas if I clearly was not on the graph and I use the up and down arrows, then I'm going to have clearly different points that I'm matching up with. One way we can also look at this is I can look at the table. If I hit second function graph, here what I see if I have different x values starting at 0 and working my way up. At x equals 1, y1 equals negative 1, and y2 equals negative 1. Now, there's also a feature we have on the calculators in the calc menu, second function trace, that allows me to find the intersection point between two graphs. Let's see how this is going to work. The first thing that it asks for is which is the first curve I want to look at. So by default, it's going to y1, y equals 2x minus 3. Now, some of you might say this is a pretty silly question. There's only two equations that are being graphed here, and both of them are straight lines, so why should it bother asking me which is the first and which is the second? Well, first off, it can graph up to 10 different equations at the same time. So it does want to make sure that we can intersect these graphs at the ones that we actually want. Now, the other thing is it doesn't know off the top of its head that these are actually straight lines. So as far as the calculator is concerned, every equation that it graphs is going to be a curve. So I'm going to hit the enter button. Now it's going to jump up to y2 and ask me to verify that this is the second curve that I want to intersect it with. So I'm going to hit enter. And then it's asking me to guess. Well, why would I need to guess? It looks like there's only one possible place. And for straight lines, it really doesn't matter where we guess that point is going to be. Where that guess becomes critical is when I'm working with graphs that could intersect each other in more than one place. If you recall back to our work in the end of chapter 5 when I was looking at sine waves and cosine waves, and we would have those waves intersecting lines in an infinite number of places. So if I wanted to make sure I was finding the correct intersection point, I would use this guess feature to make sure I was zooming in close to the point that I was most interested in. And lo and behold, we have this point here is, again, the intersection at 1, -1. So now that we verify that that is our intersection point, we can definitely say with absolute certainty that the solution to our system of equations is going to be x equals 1 and y equals -1. Now, finding the solution in Desmos is even easier. So I've opened up Desmos here, and I want to show you all that you need to do. In this case, I'm going to enter my two equations up here. I'll say y equals 2x minus 3 and y equals -3x plus 2. Now, the plus side with Desmos, as I mentioned earlier, is that if your equations aren't in y equals form, you could just enter them in to Desmos as you see them here, but I will show you that in a minute. So now that we have these two equations here, while I'm still highlighting this particular equation, what I'm going to do is you can see very carefully on this graph that key points on this blue graph have been readily identified. I've got the y-intercept here at 0, 2. I've got an x-intercept at 0.667, which is 2/3, comma 0. And then here, I could even click on that. It will highlight that as the intersection point 1, -1. So in some cases, if you had to do this graphically, if you have access to Desmos, either using a regular internet browser like Google Chrome or Firefox or Microsoft Edge or Safari, you can access it that way, or there is an app that you can download to a mobile device and work this app directly from there. This solution comes pretty quickly. Again, what I'm going to show you here is that these equations do not need to be in y equals form in order to get you your solution to the system of equations. So here I have it written as x plus y equals 6, x minus y equals 2. And while I'm highlighted on there, again, it'll basically get me right to that intersection point. And I can even get these points here, that x-intercept and a y-intercept. But I can only get those points while I'm highlighting this equation. If I jump to the other equation and I just click on this one here, what it will want to focus on are the key points on this graph. Since it's on both graphs, it really doesn't matter, but yeah, you can see it still gets us that intersection very quickly. Now let's do an example involving the substitution method. The equations I'm working with in this example are going to be 2x minus y equals 1 and x plus 2y equals -7. As I mentioned earlier, the first thing you'll need to do is solve one of the equations, either for x in terms of y or y in terms of x. It doesn't really matter which, so you can pick whichever looks easiest. In this case, I see the bottom equation is x plus 2y equals -7. So all I have to do to get that one into x equals form is move the 2y to the other side to get x equals -7 minus 2y. From here, we want to substitute the known expression into the second equation so we can solve for one of those variables explicitly. So we've got our second equation, 2x minus y equals 1. And I know that x equals -7 minus 2y. So we'll plug that in for x to get 2 times the quantity, -7 minus 2y, all minus y equals 1. Distributing the 2 will give us -14 minus 4y minus y equals 1, which then we can combine the like terms to get -14 minus 5y equals 1. Moving over the 14 gets you negative 5y equals 15, and then dividing out the negative 5 gets you y equals negative 3. Now we'll use this answer and plug it into the other equation so we can solve for x. So if x plus 2y equals negative 7 and y equals negative 3, then x plus 2 times negative 3 will equal negative 7. Multiplying the 2 by negative 3 will give you x minus 6 equals negative 7, which then we can add 6 to both sides of the equation and end up with x equals negative 1. Again, we can verify our answer pretty quickly if I take both of these equations, plug them into Desmos, and have a quick graph generated where we can easily find the intersection point. But both through the substitution method and through looking at this graph, we should be able to easily see that the solution to this system of equations will be when x equals negative 1 and y equals negative 3. Now let's try doing a problem involving the elimination method. Suppose our system looks like this: 3x plus 5y equals 2, and 2x minus y equals negative 3. Neither of these equations is a great candidate for the substitution method, although the second equation wouldn't be too bad to turn into y equals form. But what I want to do here is multiply one equation or the other, or sometimes when we're doing this process, we may need to multiply both equations by some constant that will allow one set of coefficients to be the same as each other or the opposites of each other, so that when we combine the two equations together, one of the variables is going to fall out. Here I'm going to multiply the bottom equation by 5, because I see if I did that, I'm going to have a minus 5y in the bottom equation that I can combine with the plus 5y in the top equation. Then when I add the two equations together, that will allow the y terms to cancel out completely. Doing this makes our bottom equation turn into 10x minus 5y equals negative 15, which is algebraically equivalent to 2x minus y equals negative 3. From here, we're going to combine the two equations by addition. There's going to be some times that you may want to subtract the two equations to get things to cancel, but if I have my two variables that I want to eliminate having opposite signs, like plus 5y and minus 5y, we can just add the two equations to each other, and that will make the y's in this case fall out, so I have 13x equals negative 13. When we divide out everything by 13, you'll get x equals negative 1. Now we'll use that answer that we just got for x to solve for y. We could plug this value, x equals negative 1, into either equation. It doesn't really matter. So I'm just going to plug it into the first equation, 3x plus 5y equals 2. When x equals negative 1, we substitute that in, makes this become negative 3 plus 5y equals 2. Adding 3 to both sides gets you 5y equals 5, which then if we divide everything by 5, gets you y equals 1. So there is our solution: x equals negative 1, y equals positive 1. Again, doing a quick check on Desmos will show you that the crossing point of these two lines represented by these two equations will be the point negative 1, 1, which means this, again, the solution to this system of equations will be x equals negative 1 and y equals positive 1. Let's look at a slightly different example. What if our two equations were 3x minus 2y equals 6 and negative 6x plus 4y equals 12? Let's use the elimination method where we were going to multiply the top equation by some constant that will allow stuff to cancel out. In this case, we can multiply the top equation by 2, which will make the 3x become a 6x, and I can see that it will cancel right away with the negative 6x in the second equation. So if I multiply the top equation by 2, I have 6x minus 4y equals 12. I want to combine that with the bottom equation, negative 6x plus 4y equals 12. When we combine these two equations in order to eliminate some of the variables, what happens is that both the x and the y fall out, leaving us with 0x plus 0y equals 24, which for all intents and purposes becomes just 0 equals 24? So what does that mean in the context of this problem? Well, essentially, it means that this problem has no solution, or rather, a solution to this problem can only exist whenever 0 equals 24. And since that can never happen, there must be no solution. This might seem a little disconcerting, so I'm going to pull up Desmos here and we'll try to graph these equations. And what you'll see is that the two lines that are represented by the equations are parallel to each other. The problem with this is that if we're saying that the solution to the system of equations is going to be at the intersection point between these two lines, and the lines are parallel, then there is no intersection point. And therefore, there cannot be a solution. There are no two numbers, x and y, in the real number system such that when you take 3x minus 2y, you would get 6, and at the same time, if you took negative 6x and added 4y, you'd get 12. We call this situation, when this happens, inconsistent. And when you see in your textbook, it will ask you, describe if there is one solution or the system is inconsistent or the system is independent. If you have two parallel lines, then that is what we're calling inconsistency. Let's do a slight twist on this last problem. Now let's say that we have 3x minus 2y equals 6, and I have negative 6x plus 4y equals negative 12. I want to take the same approach as before, where we want to use the elimination method, and we're going to multiply the top equation by 2, which will get both the x and y values to line up the way that we want to. When we combine the two equations together now, what we're going to see is that those x's and y's both cancel out, but also the constant terms are going to cancel out. And what I'm left with is 0 equals 0. So now we have to wonder again, what are we supposed to do with this? This case tells me that what we have is many solutions, or rather that this system will have a solution whenever 0 equals 0. So again, if you're not totally comfortable or having a difficult time visualizing what's happening here, let's go ahead and graph this one in Desmos as well. What we see here is when I graph these two equations, they're right on top of each other. So ultimately, they're going to reduce to being the same equation. So if the solution of the system of equations is going to be the point where the two lines cross, and the two lines are right on top of each other, then there's going to be an infinite number of solutions to this system. Now, this kind of system of equations are something we're going to call dependent. So if the two lines are right on top of each other, then the system is going to be dependent. If the two lines are parallel, it's inconsistent. Otherwise, we have one unique solution. So summing up, when you have two linear equations with two unknown variables, x and y, we have three different ways we can solve the systems of equations if you consider the graphing method, the substitution method, and the elimination method. We also have three different types of solutions that will show up. We have the case where there will be one unique solution, which graphically represents the crossing point between two graphs. We have cases where there's no solution, which we call inconsistent, and that happens when the two lines are parallel. And we have a third case, which we just saw on the last slide, which we call dependent, where there are an infinite number of solutions present because the two lines are right on top of each other. Let's look at a few application problems that will be similar to ones you will see on your homework. Here's our first example. For a wedding, Celia bought several dozen roses and several dozen carnations. Roses cost $15 per dozen, and carnations cost $8 per dozen. Celia bought a total of 17 dozen flowers and paid a total of $192. How many roses did she buy? Set up and solve a system of equations. The first thing you need to do is to try to define the key variables that you're trying to solve for and label them with some letters, possibly x and y, possibly something else if it makes more sense to use a different letter. For example, for roses and carnations, you might use the letter R and the letter C. Next, we'll set up two equations, or more if warranted, based on the constraints written in the problem. After we have it set up, we'll solve the system of equations using the most efficient method possible, maybe the elimination method, maybe the substitution method, maybe the graphing method, and then answer the question that was asked in the word problem. For this problem here, we're trying to figure out how many roses were bought, but we also don't know how many carnations were bought either. So we're going to set up two variables. Let's let x be the number of roses and y be the number of carnations that Celia bought. Now, since these problems are all giving units by the dozen, we're going to simplify our problem by letting our values of x and y also be measured by the number of dozen flowers. Otherwise, we're going to have to multiply stuff by 12. The numbers are going to get really big, and it's really just not worth it. So now we know there were a total of 17 dozen flowers purchased. So we can set that up in one equation as x plus y equals 17. Next, we know that roses cost $15 per dozen and carnations cost $8 per dozen. So that's going to create a second equation, 15x plus 8y equals 192. Now we have our two equations. We need to still solve for x and y. These numbers are looking pretty big to deal with something graphically, so I'm going to stay away from Desmos on this one, but you don't have to stay away from Desmos if you don't want to. I do see in the top equation, I've got x plus y equals 17, which if I have to turn that into y equals form to do the substitution method, that won't be so bad. So let's move the x to the other side in that equation so we can have y equals 17 minus x. Next, let's substitute that expression for y into the second equation. That will give us 15x plus 8 times the quantity 17 minus x equals 192. Distributing the 8 gives us 15x plus 136 minus 8x equals 192. Combining like terms gets this down to 7x plus 136 equals 192. Moving over the 136 to the other side makes this 7x equals 56, or x equals 8. To finish solving the system of equations, we can plug the 8 back in for x into one of the original equations, like y equals 17 minus x, to get y equals 9. Now we have the algebraic solution to the system of equations, x equals 8, y equals 9. However, this is a word problem. So the question of the day, we always have to make sure we go back and answer the question being asked. What is the question we want answered? We're asked how many roses that Celia bought. Since we've clearly labeled up here that roses represent x and x is being counted by the dozen, we can express our final answer by saying that Celia bought 8 dozen roses. And if we were asked, we could also say that she bought 9 dozen carnations. So, looking at this process, once we're able to identify what it is we're trying to solve for, we've identified our variables and set up 2 equations, this really shouldn't have been too bad to solve out. Here's another example. You and a friend go to Taco Bell for lunch. You order 3 soft tacos and 3 burritos, and your bill totals $11.25. Your friend's bill is $10 for 4 soft tacos and 2 burritos. How much do soft tacos cost? How much do burritos cost? Set up and solve a system of equations. The approach is going to be the same, so perhaps I should let you pause this video and see if you can try this one on your own. I've left the main instructions here to follow along with so you can more easily try this one on your own. So the first thing we need to do is set up variables to identify what it is we want to find out. And well, what we want to know is how much do soft tacos and burritos cost? Well, so now what we'll say is x equals the cost of a soft taco and y will equal the cost of a burrito. From your order, we know that 3 tacos plus 3 burritos equaled $11.25. So with that, I'll have the equation 3x plus 3y equals 11.25. From your friend's order, we know I have 4 tacos and 2 burritos together cost $10. So that's going to give me this equation 4x plus 2y equals 10. This looks like a good candidate for the elimination method because neither one of these equations is going to convert easily into x equals form or y equals form. So I'm going to multiply the top equation by 2 and the bottom equation by -3. I'm picking these values because doing so will make the top equation 6x plus 6y equals 2250, and the bottom equation will be -12x minus 6y equals -30. This way, the plus 6y in the first equation is going to cancel out with the minus 6y in the bottom equation when I combine the 2 equations with each other. Doing this will end us up with -6x equals -7.5, which when we divide by -6 will get us x equals 1.25. In the context of the word problem, since x stands for the cost of a soft taco, we know that soft tacos must cost $1.25. Now we can use this fact to go back and solve for the cost of a burrito. In the second equation, your friend bought 4 tacos and 2 burritos and spent $10. Well, if a soft taco costs $1.25, we can substitute that into the equation. Take 4 times $1.25 is $6 plus 2y equals 10. Moving over the 6 and dividing by 2 will get you y equals 2. Y, of course, represents the cost of a burrito. So what we can now easily say is that the soft tacos cost $1.25 and the burritos are going to cost $2 even. Let's look at one final example. Yummy's Candies sells candy in large bins. Each bin normally contains one type of candy, but a customer dumped the gumballs and the mega jawbreakers into the same bin. The sales clerk checks the sales records and knows the bin must contain 847 pieces of candy. He weighs the bin and finds it weighs 2,851.9 grams. Knows an individual gumball weighs 2.5 grams and an individual jawbreaker weighs 4.2 grams. How many of each type of candy are in the mixed up bin? Set up and solve a system of equations. Now, of course, you're wondering, why would I even wonder? Well, I guess we're assuming here that the gumballs and the jawbreakers look exactly alike so that they'd be completely indistinguishable, and that the store is going to make the customer buy the entire bin. So our approach is actually going to be pretty much the same. We need to define 2 variables that will represent our unknowns here. In this case, we can say that x equals the number of gumballs and y equals the number of jawbreakers in the combined bin. We know that altogether there are 847 pieces of candy, so that will imply we have one equation that could be x plus y equals 847. We also know the weight of each piece of candy. So if gumballs weigh 2.5 grams and jawbreakers weigh 4.2 grams, then we can say that the total weight of all the candy, 2.5 times x plus 4.2 times y, will equal 2,851.9 grams. Why don't you pause the video for a bit and see if you can figure out the solution to this system on your own now that we have these equations in hand. This is going to be another good candidate for the substitution method. We can take that top equation and turn it into y equals 847 minus x. Then we can substitute that in for y in the second equation. From here, we'll distribute the 4.2. Then we can combine the terms to get negative 1.7x plus 3,557.4 equals 2,851.9. From here, we can isolate x by subtracting the 3,557.4, and then we can divide out by the negative 1.7, which will give us x equals 415. Now that we have x, we can substitute that into our first equation so that y will equal 847 minus 415, which simplifies to 432. From here, we want to make sure we're still answering the question which was originally asked. How many of each type of candy are in the mixed up bin? Well, the bin will contain 415 gumballs and 432 jawbreakers. Again, I am hoping that for most of you in here that this material was review and that you're going to find this to be a good break from dealing with anything pretty intense. There's no trigonometry here, there's no vectors, we're back to dealing with straight lines. And honestly, I'm not sure why there's such a focus on this particular material in this course because while you do have some systems of equations to solve in calculus, they usually aren't this simple. But maybe dealing with the simplest equations will help you build some confidence for the harder ones. Ultimately, it can still come down to the golden rule of graphing. You know that every point on the graph of an equation is the solution to one equation. What we have is the graphs of two equations, and what we're looking for is the point that is in common to both graphs. The common solution to both equations is the solution to this system of equations. In the next lesson, we'll expand on this concept and look at ways that we can solve larger system of equations, perhaps with 3 or more variables. Well, before we get to that point, let's look at the problem challenge problems for this section. As a reminder, this is not material that is going to be on Quest 6. It is only going to be on the final exam. But we will be reviewing this material in class anyway. Thanks for watching, and we'll see you all soon.